Hello and welcome. The relentless tick of a clock, the feeling of time flying by or dragging on. We all experience it every single day. We live our lives by this constant, unwavering flow. But what if the very nature of time, the one thing we think we can rely on, is the universe's most profound illusion? Before we begin, take a moment to get comfortable and feel the space you're in. Where are you watching this from? And what time is it where you are? Let us know in the comments below. And while you're there, if you enjoy this journey into the unknown, please remember to hit that like button and subscribe to our channel for more mind-bending content. Because we're about to explore a reality far stranger than you can imagine. A place where the past isn't gone, the future isn't unwritten, and the moment you're living right now is the ultimate mystery. Chapter 1. Time's Ubiquitous Illusion. The clock on the wall, its second hand, a relentless, unwavering metronome, ticks away the moments of your life. Tick-tock, tick-tock. It's a sound so common, so ingrained in our existence, that we rarely stop to consider the profound mystery it represents. We live our lives by this ticking. We rush to appointments, we wait for a bus, we count down the days to a holiday. We measure our lives in years, and we feel a pang of nostalgia for the moments that have passed. We say that time is running out, that we are wasting time, or that we are making up for lost time. We speak of time as if it were a river, a tangible entity flowing from a source we call the past, through a present that is a fleeting instant, and into a future that lies ahead. This mental model, this simple linear progression, is the bedrock of our human experience. It is the framework upon which we build our memories, our plans, our very sense of self. But what if this river is an illusion? What if the ticking clock is a lie? What if time, the most constant, most fundamental, and most mysterious aspect of our reality, is not what it seems? Imagine for a moment that you are a child again. The summer days stretched on forever, a seemingly endless expanse of sunshine and play. The wait for Christmas morning felt like an eternity. Now, as a grown-up, a month can feel like a fleeting moment. A year can pass in the blink of an eye. This is our first clue that something is amiss. Our perception of time is subjective, malleable, and deeply tied to our psychological state. When we are bored, time crawls. When we are having fun, it flies. But the clock on the wall, the atomic clock in a laboratory, and the orbits of the planets all tell us that the seconds, minutes, and hours are passing at a constant rate. So which is real? Our feeling that time is speeding up, or the clock's unwavering tick? This is the first layer of the enigma we will unravel. We are not just talking about the psychological experience of time, but its physical reality. Let's take a journey back in time, not with a time machine, but with our minds, to a time before clocks and calendars. Early humans marked the passage of time by the rising and setting of the sun, the phases of the moon, and the changing of the seasons. These were cycles, not a linear flow. The concept of progress was less defined. The hunter-gatherer was caught in a repeating cycle of birth, life, death, and renewal. Time was a circle, not a line. It was only with the advent of agriculture and civilization that humanity began to truly think of time as a linear progression. We started to plan for the future, to plant crops and store food for the winter. We created calendars and sundials. We began to measure time in a more precise way, to divide it into smaller and smaller increments. We built civilizations upon the idea that the future is distinct from the past, and that we can move forward, building upon what has come before. This linear model of time, this arrow of time that points from the past to the future, became an essential tool for human progress. It allowed us to organize our lives, our economies, and our societies. But did we, in our quest to measure it, invent time as a concept and then mistake it for a fundamental reality? Consider the scientific perspective. For centuries, even millennia, scientists and philosophers alike have treated time as a backdrop, a stage upon which the events of the universe unfold. Isaac Newton, the great physicist who gave us the laws of motion and gravity, believed in what he called absolute time. He envisioned time as a universal, unchanging, and uniform flow, a kind of cosmic clock that ticked at the same rate for everyone, everywhere. In this view, time was a container, a separate dimension independent of the matter and energy within it. You could move through space, but you were just a passenger on the unyielding river of time. This was a comforting, intuitive picture of the universe. It made perfect sense to us, and it worked beautifully for describing the motion of planets and falling apples. But then, a young patent clerk in Switzerland named Albert Einstein shattered this comforting illusion. His work, The Theory of Relativity, showed that time is not absolute. It is relative. It is not a fixed backdrop, but an active participant in the cosmic dance. It is tied to the very fabric of the universe, and it can be stretched, compressed, and even warped. This is where our journey into the mystery of time truly begins. The first mind-bending concept from Einstein is what he called time dilation. He showed that time can slow down for an object that is moving very fast. Imagine two people, identical twins, born at the same moment. One stays on Earth, and the other gets into a spaceship and travels at a speed close to the speed of light. From the perspective of the person on Earth, the twin in the spaceship is experiencing time more slowly. When the spacefaring twin returns to Earth, they will be younger than their sibling. This isn't science fiction, it is a proven fact. We have observed this with atomic clocks on airplanes, and it is a crucial consideration for the GPS satellites that orbit our planet. The clocks on those satellites, moving at high speeds, experience time slightly differently than the clocks on the ground. Without accounting for this time dilation, your GPS would be off by miles every single day. This is a powerful demonstration that time is not universal. It is not the same for everyone. It depends on your speed. This is a profoundly unsettling idea. It means that there is no single, objective now for the entire universe. Your now is different from the now of an astronaut in the International Space Station, which is different from the now of a particle moving at a fraction of the speed of light. This challenges our very notion of a shared reality. If our now is not the same, how can we truly share a moment? But Einstein's revolution didn't stop there. He also showed that time is intertwined with space, forming a single, four-dimensional entity called space-time. Think of it like a giant trampoline. If you place a heavy bowling ball in the middle, it will create a curve or a dent. This is what a massive object, like a planet or a star, does to the fabric of space-time. It creates a gravitational well. Now, if you roll a marble nearby, it will follow the curve created by the bowling ball. We call this gravity. But in Einstein's view, it is simply the curvature of space-time. And here's the kicker. This curvature doesn't just affect space, it affects time as well. This leads to the second mind-bending concept, gravitational time dilation. Time slows down in a strong gravitational field. If you were to live on a planet with a much higher gravity than Earth, your time would pass more slowly. Imagine again our two identical twins. One lives on Earth, and the other lives in a hypothetical world with a much stronger gravitational pull. The twin in the high-gravity world would age more slowly. Again, this isn't just a thought experiment. It has been proven. Clocks at the top of a mountain, where the gravitational pull is slightly weaker, tick slightly faster than clocks at sea level. The effect is minuscule, but it is there, and it is a constant reminder that time is not a separate entity, but an integral part of the fabric of space-time, and it is affected by everything that happens in the universe. So we have a clock that ticks differently depending on how fast you are moving and how much gravity you are experiencing. This is a far cry from the universal, unchanging clock that Newton envisioned. It's a bit like a cosmic symphony where every instrument plays at a slightly different tempo. Our everyday experience of time is just one tiny, local, and incredibly distorted slice of this cosmic reality. We are like ants on a giant sheet of paper, only able to see a small part of the folds and curves. This brings us to a crucial question. If time can slow down and speed up, what does that mean for the arrow of time, that seemingly irreversible march from past to future? We experience time as a one-way street. We remember the past, we live in the present, and we anticipate the future. We can't go back and unbreak a vase or unring a bell. This is where the concept of entropy comes in. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that the entropy of a closed system can only increase over time. In simple terms, things tend to become more chaotic and disordered. A clean room gets messy, a hot cup of coffee cools down, and an egg, once scrambled, can never be unscrambled. This increase in entropy seems to be the very thing that gives time its direction. It's the reason we remember the past and not the future. The universe is on a one-way path toward increasing disorder, so while time might be flexible and relative, its direction seems to be fixed. But even this seemingly simple idea is riddled with paradoxes. At the quantum level, the level of atoms and particles, the laws of physics are time-symmetric. This means that the equations that describe the motion of a particle look the same whether you run them forward or backward in time. A particle's journey from point A to point B is just as valid in reverse. This is a huge contradiction. Our everyday world is governed by the arrow of time, but the fundamental building blocks of our reality don't seem to care about it at all. It's as if a grand symphony is playing, but the individual notes are not bound by the flow of the music. So we are left with a profound paradox. We experience time as a constant, linear flow. We have built our civilizations around this idea, but the laws of physics, from the vastness of the cosmos to the tiniest subatomic particles, tell us a different story. They tell us that time is not a separate entity, but a dimension intertwined with space, capable of being warped and stretched. They tell us that time's direction, its arrow from past to future, is not a fundamental law, but an emergent property, a statistical consequence of a universe tending towards disorder. This is the central mystery we are about to explore. We will journey from the Big Bang, where time itself began, to the strange and counterintuitive world of quantum mechanics. We will confront the possibility that the past, present, and future all exist simultaneously, and we will speculate on the ultimate fate of time in a dying universe. By the end of this journey, you will not have a definitive answer to the question, what is time? But you will have a new, and perhaps unsettling appreciation for the profound depth and complexity of this ubiquitous illusion. The ticking of the clock will never sound the same again. It will become a constant reminder of the most profound mystery of our universe, a whisper in the dark that asks, is time a river, a circle, a dimension, or simply a trick of the mind? Chapter 2. The Cosmic Clock, Time, and the Big Bang. If the clock on your wall is an unreliable narrator of time's true nature, a trick of our perception and motion, then where did this strange, flexible dimension come from? We've unraveled the illusion of its constancy, but we haven't yet addressed its origin. To do that, we must venture to the beginning of everything, the moment when not just matter and energy, but time and space themselves were born. We must travel back to the Big Bang. Let's be clear about what we mean by the Big Bang. It is not, as is often imagined, a colossal explosion of matter and energy into an empty space that already existed. That is a common and understandable misconception. Instead, the Big Bang was the simultaneous creation and expansion of space, time, matter, and energy from a single, infinitely hot, infinitely dense point. The question, what was there before the Big Bang, is therefore a bit like asking, what is north of the North Pole? The concept of before itself breaks down. If time began at that moment, there was no before to speak of. Our language, our very framework for thinking about cause and effect, is tied to the existence of time. So a moment before time is a moment our minds cannot truly grasp. It's a point where all the laws of physics we know, from gravity to light, cease to have meaning. It was a singularity, a place of ultimate weirdness and unimaginable extremes. Imagine the universe as a loaf of raisin bread baking in an oven. As the dough rises and expands, the raisins embedded within it all move away from each other. An ant sitting on one raisin would see every other raisin moving away from it. The ant isn't at the center of a cosmic explosion. It's just that the entire loaf is expanding. The Big Bang was like the rising of that dough, but on a cosmic scale. All of space itself has been expanding, stretching, and growing ever since that moment, carrying all the galaxies and stars within it. And with that expansion came the unfolding of time. This idea that time began with the universe is one of the most profound concepts in all of cosmology. It means that time is not a separate river flowing through a pre-existing universe. It is a river that was born with the universe and is inextricably linked to its very fabric. It is a dimension, just like the three dimensions of space: up, down, left, right, forward, back. But it is a dimension we can only travel in one direction. This brings us back to the idea of space-time, which we introduced in the previous chapter. Think of space-time not just as a flat trampoline, but as a dynamic four-dimensional fabric that was born from a single point. In the first fractions of a second after the Big Bang, the universe was a primordial fireball of unimaginable heat and energy. It was a state of incredible order, a kind of perfect, undifferentiated soup of particles, and from that initial low-entropy state, the universe began to expand, cool, and differentiate. Stars formed, galaxies coalesced, and complex structures emerged. This process of moving from a simple, ordered state to a more complex, disordered state is the key to understanding the arrow of time from a cosmic perspective. We talked about entropy in the last chapter, the tendency of things to move from order to disorder. An ice cube melts, a clean room gets messy, and a scrambled egg never goes back to its original state. The universe, since the Big Bang, has been on a one-way journey of increasing entropy. It started as a tightly packed, perfectly ordered bundle of energy, and it has been spreading out, cooling down, and becoming more and more disordered for nearly 13.8 billion years. This cosmic march towards disorder is what gives time its direction. The arrow of time is a thermodynamic arrow, driven by the universe's relentless expansion and its journey towards a state of maximum entropy. We remember the past and not the future because the universe itself has a clear one-way trajectory. The past is a state of lower entropy, and the future is a state of higher entropy. One of the most remarkable pieces of evidence for the Big Bang, and therefore for the birth of time, is something called the cosmic microwave background, or CMB. Imagine you're standing in a room and you hear a faint whisper from every direction at once, a ghostly echo of the moment the room was built. The CMB is like that, but on a cosmic scale. It is a faint uniform glow of microwave radiation that fills the entire universe. It is the afterglow of the Big Bang, the light from the primordial fireball that has been stretched and cooled by the universe's expansion for billions of years. When we look out into space and detect this glow, we are literally seeing the baby picture of our universe, a snapshot from just 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely. The existence and properties of the CMB are a stunning confirmation that the universe had a hot, dense beginning, and therefore that time itself had a beginning. It is a fossil of time's birth, a silent testament to its origin. Now let's connect this grand cosmic story back to the idea of space-time's curvature, which we introduced with the trampoline analogy. Gravity, in Einstein's view, isn't a force pulling us down, but a manifestation of the curvature of space-time. In the early universe, gravity was the dominant force, shaping the very flow of time on a cosmic scale. The immense gravitational pull of matter and energy, as it began to coalesce into galaxies and clusters, warped the space-time around it. This warping affects time. A clock near a massive galaxy or a supercluster of galaxies would tick slightly slower than a clock in a more empty region of space. To understand this on a more extreme scale, let's talk about black holes. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. It is a place of infinite density, a point where space-time is so dramatically warped that it creates a kind of cosmic whirlpool. As you get closer and closer to the event horizon, the point of no return around a black hole, gravitational time dilation becomes more and more extreme. From the perspective of a distant observer, your clock would appear to tick slower and slower. As you cross the event horizon, your time would appear to stop altogether. But for you, the person falling into the black hole, time would feel perfectly normal until you were spaghettified by the immense tidal forces. This is a dramatic, real-world example of time being not a constant, but a flexible, physical entity that is warped by the presence of matter and energy. A black hole isn't just a gravitational vortex. It is a time vortex. It is a place where the cosmic clock is so twisted that it seems to break. This leads us to a fascinating question. Is the universe running on a single cosmic clock, or are there countless local clocks, each ticking at its own rate? The answer, according to modern physics, is the latter. There is no master clock, no single universal time that governs everything. Every single location in the universe has its own proper time, a time that is measured by a clock at rest in that location. Your proper time is ticking away right now, but it is ticking at a different rate than a clock on Mars, a clock on the International Space Station, or a clock near a black hole. So, the Big Bang wasn't just the beginning of space and matter. It was the birth of this intricate, interconnected network of local clocks, all ticking at different rates, all woven into the flexible fabric of space-time. And the expansion of the universe, driven by this increasing entropy, is the grand cosmic metronome that gives time its direction. The tick-tock of your wall clock is a faint echo of this cosmic process, a localized manifestation of a universal tendency towards disorder. But what does this mean for our perception? We live in a world where the effects of relativity and gravitational time dilation are so small that we never notice them. On Earth, at our speeds, and in our gravitational field, the differences are measured in nanoseconds. Our brains are hardwired to experience a linear, forward-moving flow of time. We have to in order to function, to plan, and to survive. But the universe doesn't care about our psychological needs. It is operating under a different set of rules. Think about a river again. A person standing on the bank sees the river flowing at a constant speed. But what if you were a tiny boat on the river, and the river itself was made of a strange substance that got thicker and thinner, and had whirlpools and rapids? Your speed would change depending on where you were in the river. You might experience the flow as speeding up or slowing down. Now imagine that the river itself was created in a cosmic flood and has been expanding and becoming more turbulent ever since. Our experience of time is like being that tiny boat. We see the flow, but we are unaware of the deep physical currents and eddies that warp its very nature. The creation of the universe from a single point of zero size and infinite density, the birth of space-time, and the cosmic arrow of time are all interconnected. They tell a story not just of a physical creation, but of the creation of the very dimensions in which that creation can unfold. It is a story that forces us to let go of our most basic assumptions about reality. It tells us that time is not a backdrop, but a dynamic player, a character in the grand story of the cosmos. And this cosmic clock, born in the Big Bang and ticking away through the expansion of the universe, is a testament to the fact that time is a physical property, a fundamental part of our reality that is affected by everything. It is not just an idea in our minds, it is the very fabric of our existence. But it is a fabric that is stretched and pulled, warped and bent by the matter and energy within it. In the next chapter, we will dive deeper into the rules of this strange fabric, the mind-bending principles that govern its twisting and stretching, and the profound implications they have for our understanding of reality, our sense of a shared present moment, and the very possibility of traveling through time. We will explore the cosmic rulebook, written by Einstein, that dictates time's strange and beautiful dance. Chapter 3: Time's Twisted Twin, the Theory of Relativity. In the last chapter, we left the comfort of our everyday experience and journeyed to the dawn of the universe, discovering that time and space were born together in a cosmic fire, expanding relentlessly and shaping the very direction of our reality. We learned that time is not a pre-existing container, but a dimension woven into the fabric of the cosmos. Now we must ask, what are the rules that govern this strange, stretchy fabric? If time can be warped and bent, how and why does it happen? To answer that, we must turn our attention to the man who single-handedly rewrote the cosmic rulebook, a man whose mind was so brilliant and unconventional that he saw a universe no one else had dared to imagine, Albert Einstein. For centuries, our understanding of the universe was built on the rock-solid foundations laid by Isaac Newton. Newton gave us a universe that was a grand, predictable machine. Time, in his view, was an absolute, universal, and unwavering river, flowing at a constant rate for everyone, everywhere. Space was an infinite, unchanging stage. You could move through space, but you were just a passenger on the unyielding linear flow of time. This model made intuitive sense, and it worked spectacularly well for everything from calculating the orbit of a planet to predicting the trajectory of a cannonball. But there was a single, stubborn paradox that Newton's physics couldn't resolve, and it involved light. Scientists in the 19th century discovered that light travels at a staggering yet fixed speed, approximately 300,000 kilometers per second, or about 186,000 miles per second. But here was the problem. If you are standing still and a car drives past you at 50 miles per hour, and a person in that car throws a ball forward at 10 miles per hour, you will measure the ball's speed as 60 miles per hour. This is simple addition. It's a fundamental part of our everyday experience. Now apply this logic to light. If a spaceship is hurtling through space at half the speed of light and turns on its headlights, you would expect the light from those headlights to be traveling at 1.5 times the speed of light, but it doesn't. No matter how fast the source of the light is moving, and no matter how fast you, the observer, are moving, you will always measure the speed of light to be the same, constant value. This was an astonishing and seemingly impossible result. It was a cosmic traffic law that broke all the rules of our intuition. Enter a young Albert Einstein in 1905, working quietly in a patent office. He didn't try to explain why the speed of light was constant. Instead, he simply accepted it as a fundamental truth of the universe and asked, "What are the consequences if this is true?" His answer was the theory of special relativity, and it was nothing short of a revolution. He based it on two simple postulates. First, the laws of physics are the same for everyone in uniform motion. This is intuitive. If you're on a train moving at a constant speed, the laws of physics inside the train, like how a ball falls when you drop it, are the same as if you were standing on the platform. The second postulate, however, was the game changer. The speed of light is a universal constant. Let's unpack the mind-bending implications of that second postulate with a famous thought experiment. Imagine a spaceship traveling at an incredibly high speed. Inside the spaceship, there is a special clock. This clock doesn't use gears and springs. It uses a beam of light bouncing between two mirrors. The time it takes for the light to travel from the bottom mirror to the top mirror and back again is a single tick of the clock. Now for the astronaut inside the spaceship, the light is simply traveling straight up and down, a simple vertical path. But for you, watching the spaceship zip past from a window on Earth, the light is doing something very different. By the time the light has reached the top mirror, the spaceship has moved forward, so the light has to travel a diagonal path to get from the bottom mirror to the top mirror, and another diagonal path back down. From your perspective, the light has to travel a longer distance. Here's the crucial part. According to Einstein, the speed of light has to be the same for both you and the astronaut. If the speed of light is the same, but the light has to travel a longer path from your perspective, what gives? The answer is time. For the light to travel that longer, diagonal path at the same speed, it must take more time. Therefore, from your perspective on Earth, the light clock on the spaceship is ticking more slowly. This isn't just an illusion. If the astronaut had a twin on Earth, when the astronaut returned from their journey, they would be younger than their sibling. This is time dilation, the stretching of time due to relative motion. The faster you move through space, the more slowly you move through time. It's like a cosmic seesaw. As you gain speed in one dimension, space, you lose speed in the other, time. This is a profoundly counterintuitive idea. It means there is no single universal now. Your now is different from the now of an astronaut on a rocket, which is different from the now of a proton in a particle accelerator. Time is not a universal metronome. It is a personal experience, a relative measure that depends entirely on your frame of reference. But time dilation is not the only consequence of this strange cosmic rule. If you are traveling at high speeds, something else must give. If time stretches, then length must contract in the direction of motion. This is length contraction. A spaceship traveling at high speeds would appear shorter from your perspective. It's a bit like a cosmic funhouse mirror, where reality is twisted and warped by your speed. It's important to note that these effects are only noticeable at speeds approaching the speed of light, which is why we never experience them in our daily lives. At the speeds we travel, the time dilation is a fraction of a nanosecond, an effect so small it's imperceptible to our senses. But for things like subatomic particles in a particle accelerator, which are routinely pushed to a fraction of the speed of light, these effects are measurable and proven. For them, time truly stretches, and their lives are prolonged. Special relativity also gave us the most famous equation in all of science, EMC. TWIA. This isn't just a formula, it's a cosmic declaration. It tells us that mass and energy are two sides of the same coin. A small amount of mass can be converted into an immense amount of energy. Think of a nuclear bomb, and energy can be converted into mass. This equation revealed that mass is just a form of congealed energy, and it is a direct consequence of the interconnectedness of space and time. So, special relativity showed us that time is not absolute, but relative to your motion. But what about gravity? Special relativity only works for objects moving at a constant velocity. What happens when an object accelerates or is in a gravitational field? This was the next great puzzle that Einstein tackled, and it led to his masterpiece, the theory of general relativity, published in 1915. General relativity is where the trampoline analogy from our first chapter really comes to life. Einstein had a brilliant thought experiment he called his happiest thought. Imagine you are in a windowless elevator in deep space, far away from any gravitational source. If the elevator is accelerating upward at a constant rate, you would feel a force pushing you down against the floor, just like gravity. Now imagine you are in that same elevator, but it is falling freely towards Earth. You would feel weightless, just as if you were in deep space. This simple thought led him to a revolutionary conclusion. Gravity is not a force pulling on objects, it is the curvature of space-time. Think of a flat rubber sheet representing space-time. If you place a heavy bowling ball in the center, it creates a dent or a curve in the sheet. This bowling ball is like the sun. Now, if you roll a small marble nearby, it won't be pulled by the bowling ball. Instead, it will simply follow the curve in the rubber sheet. This curved path is what we perceive as an orbit. The Earth isn't being pulled by the sun's gravity. It's following a straight line through curved space-time. Our concept of a straight line is distorted by the presence of mass and energy. This is the profound shift in thinking that general relativity demands. Gravity is the geometry of the universe. And just as the curvature of space-time affects the path of objects, it also affects the flow of time. This is where we get a deeper understanding of gravitational time dilation. Time ticks more slowly in a stronger gravitational field. Imagine our two identical twins from the first chapter again. One stays on the ground, and the other lives on the top floor of a skyscraper. The twin on the ground, closer to the Earth's massive center, is in a stronger gravitational field. Therefore, their clock ticks slightly slower than the clock of the twin on the top floor. The effect is minuscule, a difference of billionths of a second, but it is measurable. In fact, if a clock were placed at the bottom of the Grand Canyon, it would tick a tiny bit slower than a clock at the rim. This isn't a theoretical curiosity. It is a practical reality that we must account for every single day. The GPS satellites that guide our cars and phones are a perfect example. These satellites are moving at very high speeds, which means their clocks experience time dilation and tick more slowly due to special relativity. But they are also in a much weaker gravitational field than we are on Earth, which means their clocks tick faster due to general relativity. It turns out that the gravitational effect is even stronger than the motion effect. So to ensure our GPS works, engineers have to constantly correct the satellite clocks, slowing them down to match the flow of time on the ground. If they didn't, our GPS would be off by miles every day. The fact that your phone can find your location is a daily working testament to the truth of Einstein's relativity. But general relativity has even more mind-bending consequences. It predicted phenomena that were later confirmed by observation, solidifying its place as a cornerstone of modern physics. It predicted the bending of starlight around massive objects, which was famously confirmed during a solar eclipse. It predicted the existence of black holes, regions where space-time is so curved that time itself seems to stand still at the event horizon. And it predicted the existence of gravitational waves, ripples in the fabric of space-time created by violent cosmic events like the collision of two black holes. The detection of these gravitational waves in 2015 was a monumental triumph, allowing us to hear the universe for the first time, and providing direct evidence that space-time is not static but a dynamic, flexible medium that can be stretched and squeezed by cosmic events. All of this leads us to one of the most profound and unsettling philosophical implications of relativity, the block universe theory. If time is a dimension like space, and past, present, and future are all relative to your motion and position, then what does that say about our concept of a flowing present moment? The block universe model, also known as eternalism, suggests that all of space-time, past, present, and future, exists simultaneously as a single fixed four-dimensional block. Our present moment is not a fleeting instant in a flowing river. It is simply our consciousness moving through this pre-existing block, like a spotlight shining on one frame of a movie reel. In this view, the dinosaurs still exist in their time on the block. The future, with all its events, is already there, just not accessible to us yet. The past is not gone, it is simply a different location in this four-dimensional space-time. This is a radical departure from our intuitive sense of time as a flowing river, where the future is open and the past is gone forever. It suggests that our experience of now is just a slice of a much larger reality, a reality where our free will might be an illusion, and everything that will ever happen has already happened in the cosmic sense. It is a deeply unsettling idea, one that has been debated by philosophers and physicists for a century. So, where does that leave us? We have moved from a simple ticking clock to a universe where time is a flexible, warped dimension, a twin to space, and a consequence of your speed and the gravity you experience. The clock on your wall is not a metronome for the universe, but a local measurement of your journey through this vast, dynamic, and interconnected fabric. The tick-tock is not a measure of absolute time, but a local rhythm, a dance of unimaginable precision, tied to the curvature of space-time at your very location. In the next chapter, we will delve into an even stranger realm, the quantum world, where time's behavior becomes even more bizarre, and where the arrow of time seems to vanish altogether. We will discover that at the tiniest scales, reality is even more counterintuitive and mysterious, challenging everything we think we know about cause, effect, and the nature of existence itself. Chapter 4. The Quantum Tick-Tock, Time's Bizarre Behavior at the Smallest Scales. We have journeyed from the familiar tick of the clock to the mind-bending depths of relativity, where time is a flexible dimension bent by motion and gravity. We've seen that on the cosmic scale. Time had a beginning with the Big Bang. Now we must shrink our perspective to the smallest scale imaginable, the subatomic realm of atoms, electrons, and photons. Here, the rules of reality break down in a way that is so strange, so counterintuitive, that even the greatest minds in physics have struggled to comprehend it. In this quantum world, our familiar linear flow of time seems to unravel, to blur, and in some interpretations, to vanish altogether. Imagine for a moment that you are a detective in a strange, foggy city. You know that a suspect is in a certain building, but you can't tell exactly where they are inside it. The more you try to pinpoint their location, the faster they seem to be moving, making their speed impossible to determine. This is a bit like the Heisenberg uncertainty principle, a cornerstone of quantum mechanics. It tells us that for a tiny particle, you cannot know both its exact position and its exact momentum, its mass times its velocity, at the same time. The more precisely you know one, the less you can know about the other. This isn't a limitation of our instruments. It's a fundamental, inherent fuzziness in the very nature of reality at the smallest scales. A particle doesn't have a definite position or momentum until you measure it. It exists in a blurry cloud of possibilities, a superposition of all its potential states. Now, apply this uncertainty to energy and time. The principle also states that you cannot know a system's energy with perfect precision over a perfect slice of time. This gives rise to one of the most astonishing phenomena in all of physics, quantum fluctuations. Imagine what we think of as empty space, a perfect vacuum. We picture it as a void, a nothingness. But in the quantum world, this is far from the truth. The vacuum is not empty. It is a roiling, seething sea of energy, a place where particles constantly and spontaneously pop into existence and then vanish in an instant. These are called virtual particles. They exist for a fleeting moment, borrowing energy from the vacuum, and then must repay that energy by disappearing. This is possible because of the energy-time uncertainty principle. For a very short period of time, the universe can break the law of conservation of energy, as long as it makes up for it by having the particle vanish before anyone can notice. It's like borrowing a massive amount of money from a bank for a split second before returning it. No one can prove you ever had it. This is happening everywhere, all the time, in every speck of empty space around you. It's a constant bubbling tick-tock of creation and annihilation, a bizarre dance of energy and existence. This phenomenon shows us that time, at this scale, is not a smooth continuous flow, but a pulsating, probabilistic medium. But the real mystery of time at the quantum level lies in a different, more profound paradox. As we discussed in the last chapter, our everyday world has a clear arrow of time, a direction from past to future, defined by the increase of entropy. A broken egg never unscrambles itself, but when physicists write down the fundamental equations that describe the behavior of a single particle, they are almost all time-symmetric. This means they are completely reversible. If you were to film a video of two electrons colliding, and you played that video backward, the laws of physics would be perfectly obeyed. The reverse collision is just as valid as the forward one. A particle's journey from a blurred state to a definite state can, in principle, happen in reverse. The quantum world, at its core, seems to have no built-in preference for time's direction. It is a universe without an arrow, a movie where every scene can be played in reverse without violating the laws of physics. So how do we get from this time-symmetric quantum realm to our macroscopic world, where the arrow of time is so obvious? This is one of the deepest unresolved problems in physics, known as the measurement problem. Imagine our blurry particle from before, existing in a superposition of states. It is in multiple places at once, or spinning in multiple directions at once. According to the standard interpretation of quantum mechanics, the act of observing or measuring the particle forces it to collapse into a single definite state. It is only at the moment of measurement that reality becomes solid. Before that, it is just a cloud of possibilities. This is where time seems to get its direction. The arrow of time is a consequence of this irreversible collapse from a state of superposition to a definite state. The universe is constantly making choices, collapsing possibilities into realities, and it can never go back. But what constitutes a measurement? Does it require a conscious observer, or is it simply the interaction with another particle? The debate rages on, and it links the nature of time to the nature of consciousness and observation in a deeply unsettling way. The ticking of the clock, from this perspective, isn't a fundamental process, but a byproduct of a billion trillion quantum collapses happening every second. The weirdness doesn't stop there. Let's talk about quantum entanglement. Imagine you have two quantum particles, like two electrons, that are linked in a special way. You take one and send it to the other side of the universe. Now, you measure a property of the electron in your hand, say its spin. The moment you measure it, the spin of the entangled electron on the other side of the universe is instantly determined, no matter the distance between them. This happens instantaneously, faster than the speed of light. Einstein himself famously called this spooky action at a distance. It seems to violate the fundamental rule of relativity, that nothing can travel faster than light. However, physicists have shown that this spooky action doesn't allow for communication. You can't send information faster than light using entanglement, but the event of one measurement instantly affecting the other seems to defy our sense of cause and effect and the linear passage of time. It suggests a non-local reality, a universe where objects are connected in ways that transcend space and time as we know them. It's as if the two particles are not two separate entities but part of a single unified whole, and their state is decided for the whole the moment any part is observed. Now for the ultimate challenge. We have two powerful theories that describe our universe: general relativity for the very large planets, stars, galaxies, and quantum mechanics for the very small atoms, particles. Both are incredibly successful, but they are fundamentally incompatible. When you try to combine them into a single, unified theory of quantum gravity, something astonishing happens. Time often disappears from the equations. Consider one of the key equations in the search for a quantum theory of gravity, the Wheeler-DeWitt equation. This equation attempts to describe the entire universe as a single quantum system. When you look at the equation, you find a startling absence. There is no time variable, no t for time. The equation describes a static, timeless universe. It is as if the universe is a single cosmic snapshot, a static photograph where everything is happening at once. In this view, time is not a fundamental property of the universe, but an emergent phenomenon, a kind of large-scale illusion that arises from the collective behavior of countless particles. It's like temperature. A single atom doesn't have a temperature. Temperature only emerges as a concept when you have a large collection of atoms moving and interacting. In the same way, perhaps time only emerges when you have a large collection of quantum events and collapses. This is the concept of relational time. Maybe time isn't a continuous background clock, but is simply a label for the changes that happen to matter and energy. If the universe were frozen in place with nothing moving or changing, would time even exist? Or would it be a meaningless concept? The quantum world suggests that without change, there is no time. This forces us to confront our most basic intuitions. We live in a world of clocks, calendars, and schedules. We see time flowing from a distinct past into a distinct future. But the quantum world presents a dizzying picture where cause and effect can be blurred, where the future can seem to influence the past, and where the arrow of time seems to be just a statistical illusion, a byproduct of a universe moving from a less probable state to a more probable one. It's a universe where now is a fragile concept, created moment by moment, by observation and interaction. The ticking of your clock, then, is not a fundamental tick-tock of the universe. It is the result of billions upon billions of atoms in the clock's spring or crystal moving, changing and interacting. And each one of those interactions is governed by a set of rules that are utterly timeless and reversible. The illusion of a forward march of time is simply the sum total of these countless, chaotic, and fundamentally time-symmetrical quantum events. We are built on a foundation that doesn't care about the past or the future, and yet we have a deep and undeniable sense of a one-way temporal street. This is perhaps the greatest paradox of all. In the next chapter, we will take all the mind-bending ideas we've explored, the relativity of time, the cosmic arrow of time, and the quantum blurring of time, and we will confront their most profound philosophical consequence. If the past and the future are not as distinct as we think, what does that mean for our sense of reality? We will challenge the very notion of past, present, and future, and ask whether they exist as separate entities or as part of a single, eternal reality. Chapter 5. The Paradox of the Past, Present, and Future. We have journeyed to the furthest reaches of the cosmos and the deepest recesses of the quantum world. And with each step, our intuitive understanding of time has been challenged, stretched, and blurred. We've seen that time began with the Big Bang, that it can be stretched by speed and bent by gravity, and that on the tiniest scales, its fundamental direction seems to vanish. Now we must take all these mind-bending insights and confront the most profound philosophical paradox of all, the nature of the past, the present, and the future. If time is so relative and strange, are the past, present, and future truly distinct entities, or are they all part of a single, eternal reality? Our common-sense view of time, what philosophers call presentism, is as simple as it is powerful. It's the flowing river model we started with. In this view, only the present moment is real. The past is gone forever, a collection of memories and consequences that no longer exist. The future is not yet real. It is a realm of possibilities, a blank canvas waiting to be painted by our choices. Our consciousness is a spotlight, illuminating the single moment we call now, and everything before it has vanished into the darkness, while everything ahead has yet to emerge. This model is intuitive, it aligns with our experience, and it provides a powerful foundation for our sense of free will. It is why we feel regret for the past and hope for the future. It's a very human way to look at the universe. But what happens when we confront this intuitive model with the hard truths of relativity? Let's revisit the revolutionary idea from the last chapter, the relativity of simultaneity. This is the cornerstone of the paradox. Remember our thought experiment with the lightning strikes and the moving train. For an observer standing on the ground, 2 lightning strikes hitting the ends of the train at the same moment were simultaneous. But for an observer moving on the train, the strikes were not simultaneous. The light from the strike ahead of the train had to travel a shorter distance to reach them, so they saw it first, meaning for them, that strike happened before the other. Now here's the crucial question. Which observer is right? Which set of lightning strikes is the real set? The ones that happened at the same time, or the ones that happened at different times? According to Einstein, they are both right. There is no single universal now for the entire universe. This simple fact has a truly mind-blowing consequence. Imagine you are standing on Earth, and I am on a spaceship hurtling through space at nearly the speed of light. Now imagine a distant star, 1,000 light years away. For me on the spaceship, my present moment is a different slice of space-time than your present moment on Earth. My slice of now could include events that are in your future, and your slice of now could include events that are in my past. This isn't just about what we see or perceive. It's about what is physically real. According to relativity, there is no universal here and now. My now and your now are different, and your now includes a distant star's history, while my now might include a distant star's future. If your now is just as valid as my now, and my now contains your future, then how can your future not already exist? It is as if the universe is a giant tapestry, and our now is simply the part we are looking at. But the whole tapestry, past, present, and future, is already woven. This brings us to the rival philosophical model, eternalism, also known as the block universe theory. The block universe is a direct consequence of Einstein's spacetime. In this model, spacetime is a 4-dimensional block, a single, unchanging reality where past, present, and future all exist simultaneously. Think of it like a giant loaf of bread, where each slice is a moment in time. Every slice of the loaf exists at once. From the first slice to the last, we simply perceive ourselves as moving from one slice to the next. The past is not gone, it's just a slice we have already experienced. The future is not yet real, it is a slice that we have not yet reached. To put it another way, imagine the universe as a movie reel. Every single frame of the movie, from the beginning to the end, exists on that reel all at once. The entire story is already there. Our experience of time passing is just our consciousness moving from one frame to the next, from the beginning of the reel to the end. The climactic scene at the end of the movie isn't not real just because we haven't watched it yet. It's right there on the reel, a fixed part of the story. According to the block universe, our sense of a flowing present is an illusion, a trick of our consciousness. The moment you are listening to these words, the moment of your birth, and the moment of your death are all equally real and exist as fixed points in the space-time block. All of history, from the first stars to the last dying embers of the universe, is a frozen, 4-dimensional statue. This is a profoundly difficult concept to accept. If everything is already there, already determined, then what about our feeling of free will? If the future already exists, are our choices predetermined? This is the central philosophical challenge of the block universe. If your choice to drink a cup of coffee tomorrow morning already exists in the space-time block, then was it truly a choice? This is where the debate gets heated. Some philosophers and physicists argue that free will is an illusion, a powerful cognitive trick that our brains play to help us navigate the world. Others argue that our experience of free will is too powerful to be an illusion, and therefore the block universe must be wrong. The science, however, seems to point to the block universe. If simultaneity is relative and time is just a 4th dimension, then the evidence for a single, flowing now is very weak. Another major objection to the block universe is the concept of change. If everything is fixed in the block, how can anything change? The answer is subtle but crucial. Change, in this view, is simply a difference between one slice of the block and the next. A caterpillar doesn't change over time. It exists as a caterpillar at one time slice, and as a butterfly at a later time slice. Just as a landscape contains both a mountain and a valley, the block universe contains a sequence of moments, and the difference between those moments is what we call change. It's not a process in a flowing river, It's a static sequence of events, and our perception of flow is what creates the illusion of change. But the block universe also faces a significant challenge from the quantum world, which we explored in the last chapter. How can a fixed, unchanging block contain the inherent uncertainty and probabilities of quantum mechanics? The quantum world is all about possibilities and randomness. A quantum particle exists in a superposition of states, a cloud of probability, until it is measured. How can a fixed block contain a blurry particle that doesn't have a definite state until it's observed? This is where the two great pillars of physics, relativity and quantum mechanics, collide in a fundamental disagreement over the nature of time. Some interpretations of quantum mechanics, like the many worlds interpretation, try to resolve this conflict. In this view, every time a quantum possibility collapses, the universe splits, creating a new branch of the space-time block for every possible outcome. The particle exists here, and it exists there, in parallel universes. Our experience is just a single path through this constantly branching cosmic tree. This is another form of eternalism, a growing block of realities where every possible future exists. It's a staggering concept, and it suggests that not only is your future already real, but every possible future you could have imagined is also real in a different universe. To find a middle ground, some have proposed the growing block model. In this view, the past and the present are real and fixed, but the future is genuinely open and not yet real. The block of space-time is constantly growing as new moments are added to the present. This model allows for a genuine flow of time and preserves a sense of free will, as our choices determine which future moments are added to the block. It is a more intuitive model, but it still struggles to fully reconcile with the evidence from relativity, which suggests that there is no privileged present moment for the block to grow from. So we are left with a cosmic puzzle with no easy solution. Our everyday experience and the statistical arrow of time suggest a clear distinction between past, present, and future, with the present as the only reality. The hard scientific evidence from relativity, however, points to a timeless block where all moments exist simultaneously, and the strange world of quantum mechanics adds a layer of uncertainty and probabilistic possibility that doesn't fit neatly into either picture. The ticking of the clock has brought us to this profound crossroads. We are forced to ask whether our sense of a flowing time is a deep and fundamental truth about the universe, or a powerful cognitive illusion that helps us make sense of a reality that is far more alien than we can imagine. Is the past truly gone? Is the future already written? The paradox of the past, present, and future is not just a philosophical parlor game. It is a direct consequence of the laws of physics themselves. It is the ultimate mystery of time, and it leads us to our final question. What is the ultimate fate of this strange dimension, this most constant mystery? In our final chapter, we will look to the ultimate end of the universe itself and ask what that means for time's final, silent tick. Chapter 6. The End of Time. Time's ultimate fate and beyond. To answer this, we must look to the ultimate destiny of the universe itself, and physicists have a few competing theories for how it all might end. The ultimate fate of time is inextricably linked to the ultimate fate of space, matter. We have journeyed together from the tick of a clock to the very beginning of the universe, and then down into the weird probabilistic world of quantum mechanics. We have wrestled with the mind-bending realities of relativity and the profound philosophical paradox of a universe where past, present, and future might all coexist. We are left with a deeper, more profound mystery than when we began. We know that time is not what we think it is, that it is a physical dimension, a flexible fabric, a statistical illusion, or perhaps all of the above. But now, as we reach the end of our journey, we must ask the final, ultimate question. If time had a beginning, will it have an end? What is the ultimate fate of time in a dying universe? The first and most widely accepted theory is known as the heat death of the universe, or the Big Freeze. This theory is a direct consequence of the laws of thermodynamics and the fact that the universe's expansion is accelerating. We've talked about entropy, the measure of disorder, and the cosmic arrow of time, the universe's relentless march from a state of low entropy, the Big Bang, to a state of high entropy. In the heat death scenario, This march continues unchecked. The universe keeps expanding, spreading out matter and energy, and getting colder and colder. 67. Imagine the universe as a vast cosmic cauldron. In the beginning, it was a boiling, energetic soup. But over billions of years, that soup has been cooling and spreading out. In the heat death, this process never stops. Eventually, all the stars will burn out, having exhausted their nuclear fuel. The last red dwarf stars will fade away into darkness in trillions of years. The universe will be a cold, dark place, lit only by the faint glow of the last embers of stellar life. The next cosmic objects to die will be the remnants of stars, white dwarfs, neutron stars, and black holes. Even the most powerful cosmic engines, the supermassive black holes at the centers of galaxies, are not eternal. The great physicist Stephen Hawking showed that black holes slowly evaporate by emitting a faint radiation known as Hawking radiation. This process is incredibly slow, taking unimaginable lengths of time. A black hole with the mass of our sun, years to evaporate. A supermassive black hole would take even longer, on the order of 10 years. That number is a 1 with 100 zeros after it. A span of time so vast it is utterly meaningless to the human mind. 100, 100. And what happens to time in this state? In a universe of ultimate disorder, where everything is uniform and unchanging, the thermodynamic arrow of time, the driver of the flow we experience, would cease to have any meaning. There would be no change, no order to break down, no processes to unfold. A single particle would drift for eons without ever encountering another. If time is defined by change, by events, by the unfolding of processes, then in a universe of nothing but stillness and uniformity, time would grind to a halt. It wouldn't just slow down. In a meaningful sense, it would cease to exist. The tick-tock of the cosmic clock would finally fall silent. The universe would exist in a state of eternal, motionless timelessness, a cosmic slumber from which it could never awaken. The mystery of time's direction would be solved in the most profound way possible by the complete and utter disappearance of direction. After all the black holes have evaporated, the universe will be an unimaginably cold, dark, and empty place, filled only with a dilute soup of photons, neutrinos, and perhaps a few stray electrons and protons that haven't decayed. The average temperature of the universe will approach absolute zero, and all of its energy will be spread out evenly, with no hot spots and no cold spots. This is the state of maximum entropy, the ultimate state of disorder. But what if the universe's destiny is different? The second theory, the Big Crunch, is less favored, but still a possibility. In this scenario, the expansion of the universe, which is currently accelerating, would eventually slow down and reverse. The gravitational pull of all the matter and energy in the universe would begin to dominate, pulling everything back together. The expansion would turn into a contraction. The universe would retrace its steps, getting hotter and denser. Galaxies would crash into each other. Stars would be ripped apart. And eventually, all matter would be squeezed back into a single, infinitely hot, infinitely dense singularity, a state reminiscent of the Big Bang. So what happens to time during the Big Crunch? As the universe contracts, the gravitational forces would become immense, causing time to slow down dramatically for a distant observer, just as it does near a black hole. As everything rushes towards the final singularity, the flow of time would accelerate for those in the contracting universe, but would be heading towards a definitive end. The arrow of time would still be a one-way street, but a street that leads to a dead end. Some physicists have speculated about a big bounce, where the Big Crunch of one universe leads directly to the Big Bang of the next, creating an endless cycle of cosmic death and rebirth. In this cyclical model, time would not be a line but a circle. It would have no ultimate beginning or end, only endless cycles of unfolding and refolding. The tick-tock would reset with every new universe, a cosmic metronome for a universe that lives and dies over and over again. The third and most dramatic theory is the Big Rip. This theory is based on the idea that dark energy, the mysterious force causing the universe's expansion to accelerate, will become so powerful that it will eventually overcome gravity and all the other fundamental forces. In the distant future, the expansion would become so violent that it would begin to tear apart matter. First, galaxies would be pulled apart, then solar systems, then planets. In the final moments of the universe, atoms would be ripped apart, and finally, even the fabric of space-time itself would be torn to shreds. All the distances between all particles would become infinite, and the very concept of space would cease to have meaning. In this violent end, time would be destroyed along with space and matter. The clock would not just stop, it would be shattered, its pieces scattered into an abyss of nothingness. These are just three of the potential fates of the universe, and each has a profound implication for the ultimate fate of time. But let's bring it back to the most compelling mystery from our previous chapters, the idea that time might not be a fundamental property of the universe, but an emergent phenomenon, something that arises from the collective behavior of countless particles. In the quantum world, we saw that the fundamental rules of reality are timeless and reversible. The arrow of time, the flow we experience, is a statistical illusion of a universe moving from order to disorder. It is a feature of our macroscopic reality, not a fundamental law of the cosmos. So, where does that leave us? We have explored time from every conceivable angle, and we are left with more questions than answers. We don't know what time truly is. Is it a dimension we move through, a universal flow, a static block, or an illusion created by consciousness? We may never know for sure. The greatest mystery of the universe may lie not in a distant galaxy or a subatomic particle, but in the relentless tick of a clock, a sound that is a constant reminder of the profound riddle that lies at the heart of our existence. The clock on your wall is not just a device for measuring a day. It is a portal to the cosmic beginning, a witness to the strange dance of relativity, a window into the quantum realm, and a faint echo of the universe's ultimate fate. It is a constant whisper in the silent night, a reminder that we are living in the middle of a mystery, a story with a beginning, a middle, and possibly an end to time itself. If time is emergent, what happens when the conditions for its emergence are gone? In the cold, dark, uniform stillness of a heat-death universe, where all change has ceased, what would time be? Without events to measure, without processes to unfold, without a thermodynamic gradient to provide direction, the very notion of time would dissolve. The cosmic clock would revert to its timeless, reversible, quantum state. Our macroscopic world, with its ticking clocks and flowing seconds, would be just a fleeting moment in a grand cosmic story, a brief interlude between the timeless beginning and the timeless end.